Let's start with our exploratory challenge. We are on record. So let's go over this real quick. Ladies and gentlemen, who felt good about their last test?
No.
Why did we not feel good about our last test? Could it be because we did not feel prepared?
Yeah.
Let's be prepared next time, shall we? Handout on the podium. Let's be prepared next time. The first step in being prepared is listen when information is disseminated. Okay? So let's listen. George Ferris built the first Ferris wheel in 1893. Who wants to read this for me? Who likes reading? Fine, I'll read. George Ferris built the first Ferris wheel in 1893 for the World's Columbian Exhibition in Chicago. It had 30 passenger cars. It was 264 feet tall and rotated once every 9 minutes when all the cars were loaded. The ride cost 50 cents. 50 cents. Curtis Jackson. The ride cost Curtis Jackson. Create a sketch of the height of the passenger car on the original Ferris wheel as that car rotates around the wheel 4 times. List any assumptions that you are making as you create your model. So we're going to do this. My content. Let's make this smaller. Let's everybody draw a graph. Let's everybody draw a graph. So what did it say how tall it was? It says 264 feet tall. Yes, sir. 264 feet tall. Yes, ma'am. You can draw a graph, right?
Yes.
You're artsy.
No.
You said you're going to be a graphic designer, right?
That's different.
Let's design some graphics.
That's different than drawing a graph.
So let me ask you this. It says, graph the height of a passenger car versus time as the wheel goes around 4 times. What's the highest that this car is going to get? How tall is the top of the circle, Camden? 264 feet. So, how many squares up should I put that? I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17, 18, 19. I got 20 squares. Maybe do 2. 20 per square. So 13. So 20, 40, 60, 80. Whoa. So 1, 2, 3, 4, 100. 1, 2, 3, 4, 200. 1, 2, 3, 4, 300. So this is height in feet, right? And then it says, as it goes around 4 times. And how many minutes does it take to go around once? So how many minutes should I make my x-axis? It goes around 4 times, and each time takes 9 minutes. So I need at least 36. 40 is a nice round number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I also have 20 squares here. So maybe I should do 1 square every 2 minutes. 2, 4, 6, 8, 10. So that there is 20 minutes, right? Oh no, that's 10 minutes. I'm sorry. 10 minutes. 2, 4, 6, 8, 10, 20, 2, 4, 6, 8, 10, 30, and 2, 4, 6, 8, 10 is 40. And this is time in minutes. Okay. Do we want our passenger car to start at the bottom or the top? Bottom? Okay. Do mine in red. So if it starts at the bottom, when time equals 0, my height is 0. How long does it take to get to the top? 4.5. Why 4.5, Andrew? Yeah, so in 9.5 minutes, right about there, it's going to be back at 0. But in the middle, at 4.5, I heard that. At 4.5, it's at 264, which is right about there. Now, let me ask you, is it going to be a jagged tooth like that? Is that what it's going to look like? What you're thinking, Caleb? It's not that I shoot to the top and then I shoot to the bottom, right? It's kind of smooth. It's curvy. It's curvy. So instead of being a like sawtooth, it's going to be snap. It's going to look a little bit more curvy. Forgive my crummy artwork. Now, how long before it's back to the bottom again? So I'm at 9.5, or I'm sorry, I'm at 9, and it's back to the bottom again. When does it get back to the bottom a second time? And another 9, which puts me at 18, which is right there. How long before it gets to the bottom again? 27, which is 2, 4, 6, and 7 right there. And then lastly, 36, right here. How about the top? We were at 4.5 right there. How long before it gets back to the top? 4.5 plus 9, right, Jeff? Gets me to where? 13 and a half? 12, 13 and a half is right about there. And now at 13 and a half plus another what? Plus another 9 when I'm at the top again. So 13 and a half plus 9 is, help me out, 22 and a half. So 22 and a half right about there. And then plus another 9. So 31 and a half. And then do I get to another top? Not in that 36 minutes, right? So then, this is going to do one of, Does my artwork stink or what? It's amazing. Did I hear amazing? I should say that to all the teachers. All right. What assumptions did I make when I was doing this? Let me ask you this. If the passenger car is at 0 feet, what does that mean in real life? At the bottom of what? Is that at the bottom of the Ferris wheel? Or I said height, right? Where do I measure height from? The ground, right? So if I'm at 0 feet elevation, or 0 foot height. I'm actually scraping on the ground, aren't I? Is it scraping on the ground? Hey, Ferris wheel ever seen scrape the ground? No, no. It's elevated a little bit, right? So, maybe one assumption. At 0 feet, the Ferris wheel is slightly off the ground. Let's hope, right? Is slightly off the ground. What other assumptions can I make? Is there any other assumptions I can make? Let me ask you this. How high is the center of this Ferris wheel? How do you get that, Liv? Okay. Okay. So 132 feet. So what is the radius of this Ferris wheel? Does everybody get that?
Yeah.
Radius of Ferris wheel is approximately 132 feet. Okay. Let's graph that line in here. Let's graph that line. Let's go here, and I'll do green. So it's 100, 20, 30, right about there. Does that look about right? Yeah. Good. You have a conflict, Isabel? Okay. Remind me to put that on my list, okay, so that I have record of it, okay? I don't have it yet. Thank you. All right, so let's turn the page, see what else they ask. It asks you, what kind of function would best model this situation? Is there anything that we've talked about thus far that would be the best at modeling this situation? Would a linear function be the best for modeling this? What does a linear function look like? Like that? Or like that?
The straight line.
Straight line, right? So would a linear be the best for modeling that? We need something that goes up and down, right? We looked at functions like that, didn't we? We looked at different types of polynomials. How many times did I got peaks and valleys on this, right? How many peaks or valleys did I get with a second degree polynomial, quadratic? Who remembers? Quadratic looked like this, right? Now, wrong. Quadratic looked like this, right? What happens over here? That just goes up to infinity, right? And on the other side, the same thing. Is that going to be the best idea for us? No, no. What about a third degree polynomial? Does anybody remember what a third degree polynomial? Cubic, right? Cubic looks something like this. It went up to infinity over there, went down to negative infinity over here. That looks a little bit better, right? But is that the one we want? No, no. And remember, each degree that we put on our polynomial added a little wrinkle to it. So that was a 4th degree polynomial. A 5th degree polynomial. Sixth degree polynomial, and I could go on and on and on, right? But these aren't really the best tools to model this, okay? It's not the best tool. Now, we're going to go into exercise 1. Let's suppose now that a Ferris wheel has a diameter of 150 feet. So this is a smaller Ferris wheel now, right? Smaller Ferris wheel. From your viewpoint, the Ferris wheel is rotating counterclockwise. Counterclockwise. Like this. We will refer to a rotation through full 360 degrees as one turn. So sketch the height of the car that starts at the bottom of the wheel and continues 2 turns. It's going to look a lot the same, isn't it? Create a sketch of the height of this car as it starts at the bottom. So we want it to start at the bottom and continues through for 2 turns. The top being 150 feet. We'll do each square being 10 feet, so 15 squares. 1, 2, 3, 4, 5, 5, 10, 2, 3, 4, 15. So this is 150 feet. This is 100. This is 50. So it's going to start at the bottom and continue for 2 turns. Okay? Now, notice how it doesn't tell us how much time it takes to make a turn. At least not in part A. Does it tell you? But can we make an assumption that the Ferris wheel rotates at the same rate all the time? It doesn't speed up and then slow down and then speed. I mean, after we load all the people, right? After we load all the people, it's going at a pretty steady rate. So, let's say it takes, should we say, let's say it takes 16 squares to go, or no, let's say it takes 8 squares to go through 1 turn. Why am I choosing 8? So it takes 8 squares to go through 1 turn, and 1, 2, 3, 4, 5, 6, 7, 8 squares to go through a second turn. Why do you think I chose 8? How many squares is it going to take to get to the top? If it took 8 squares to go through the whole thing, how's it going? Many is it going to take to get halfway? 4, right? And that 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6, 7, 8. From that is where it's at the top of the other turn. So, and then we connect the dots just like we did before with curvy lines. That one looks a little better. Where should I put my green line, my lime green line? Where's that? How tall is it again? My diameter is 150. So my radius is 75, right? That's where the midpoint is 75. So it asks us to explain how the features of this graph relate to the situation. What does that mean in English? It's not a very well-worded question, is it? What do you think that means? What's it doing down here? You're at the bottom. Which way are you moving? Remember, it's going counterclockwise for you, right? Which way is it moving at the bottom? It's moving pretty much that way, right? So it's moving more over than it is up, right? But as soon as it starts moving over, it starts going up a little bit by a little bit. How about when the car is here? Right on the side. Which way is it moving? It's going straight up at that point, right? It's going straight up. It's not moving back this way at all at this point. But as it goes, it's getting more and more lateral motion until up here at the top, it's all lateral motion, right? It's all going that way. And then starts going down at this point. At first it starts going down slowly, right? But then over here, it's going down relatively fast, right? That's why we see a curve and not straight jagged lines. Is because that lateral motion is getting converted to vertical motion, and then converted to lateral motion again, and then converted to vertical motion. It's not all happening at once. Okay? That's what they're looking for in part B. Okay? Now, I want to stop there because we have to do some ACT prep. I am going to give this to you. This is graded, by the way. This is going in the grade books. So, I want you guys to do this tonight. Okay? Let me...